Morning, everybody. Thank you for coming. Please call me Marco. And yeah, I'm here to try to convince you that functional programming matters in computer science education. So before I start, of course, thank you to Andy and Arthur for inviting me and the program committee and ICFP at large. And of course, all of you for coming. So for those of you who don't know me, right, I do some work as you were told in implementation of programming languages. So I've done work with lambda lifting and memoizing closures for CPS and for, in general, for functional programming languages. And then tons of stuff in computer science education, especially a curriculum for beginners, which of course I'll highlight a lot of today. And then, right, I've started a new project that is going to tackle changing the way formal languages and automata theory is taught. And hopefully, if there's enough time, I'll give you a taste of that towards the end of the talk. Okay. And of course, I am the chair of the steering committee for trends in functional programming. I'm also involved with IFL, and I'm a co-founder of Trends in Functional Programming in Education, which is inherited or comes out of functional and declarative programming in education, which was traditionally co-located with ICFP, right? And of course, I do lots of reviewing, way too much. Okay. So I want to make the talk interactive since we're such a cozy group. So feel free to interrupt with questions at any point, okay? Okay, so if we want to talk about why functional programming is important in computer science education, of course, we kind of have to agree in what's important in computer science education. And I'm sure each of us here has your own list of what's important and what can be kind of left on the back burner, right? But I'm sure that the intersection of all our lists is not empty. So I'm going to try to come up with a list here that's hopefully in our intersection, and then add a few things at the end that I think would be, right, it's good for students to learn, right? So first of all, right, students have to learn how to program, right? So they need to know how to design solutions to problems, not just hack away, trial and error, but actually think and design. And then they have to be able to express that solution in some syntax, right? Some programming language. Now, I think they also need to learn about abstraction, right? So you don't want them reinventing the wheel and writing the same code 50 times, right? So you abstract away and you write a function, and then now you have modularity, and they need to learn about this. And they need to know about iterative refinement, right? They need to know that you can't solve everything in one step, right? You don't bite off more than you can chew, proverbially speaking. And we should teach them about documenting their programs, right? Don't give somebody code with no documentation or without tests. So in my classroom, for example, right? I mean, you write a program without unit testing, it's not a program, right? So it's important to always validate your code. And then, of course, we want them to know about efficiency and complexity when it comes to picking between choices or between designs. And then I think that's in our intersection. And then, right, I would like students to learn more about empirical experimentation, right? How to run numbers, right? And teach them about, right, simple stuff like averages and relative difference and standard deviation, and be able to pick, right? To study, right, the comparison between performance between two different algorithms. And then it should be fun, right? Above all, it should be fun, right? Students should have a ball with this. They should have a blast. And having fun it does not exclude being rigor, right? Having rigor. Yes, Simon.
So if you title this slide, what is important in programming education, all of these things would make sense.
Yes.
So do you think there's any difference between those two titles?
Which ones, I'm sorry?
What's important in programming education? What's important in computer science education?
No. I haven't
made. Co-terms.
Yeah, I'm
teaching computer science equals teaching programming.
Not entirely, but there's a huge overlap there.
Cool. Yeah. I think of programming is like the practical work, the practical lab work of the natural sciences.
Yeah.
But it's not coterminous.
Yeah. I agree. Okay. And then I think that you have to teach them stuff that's relevant, right? New stuff that's current right now. So, for example, distributed programming, which is everywhere, right? Students should kind of learn this naturally not as an afterthought. Okay, so if we can agree that more or less all of these things are important, right? The question is, can this be done with a functional programming language now? And, right, can all of this be done, in my case, with beginners? Right? Can we take a bunch of first-year students and say, look, learn this stuff right here. You're going to learn about all of this stuff. And so to me, the answer is an unequivocal yes, right? And I argue, and hopefully I'll convince you today, that it's easier to do all of this stuff with a functional programming language, but it's not for free. And it's not for free because the world is full of people who don't know anything about functional programming. And so you hit them with something like this and, they don't know. So a lot of new upcoming young faculty, right, they have a real hard time learning, right, how to express solutions to problems using a functional programming language. Yes.
Is this implicitly what's important in computer science education for undergraduates? Or
yes. Yes.
So I'm interested in functional programming education, the programming education for 6-year-olds, but that's not in your scope. You might have different answers to many of these questions. Yes. Right. So you're thinking undergraduate.
I'm thinking undergraduate.
Okay, fine, yes. Thanks.
Okay. So surprisingly, right, many textbooks don't do this stuff, right? They just don't. And in fact, they do the contrary to what we feel if we agree that these things are important. And I just want to highlight what I mean by that, right? So I'm going to give you this code here, right? It's quicksort, right? I kind of right? We all know quicksort, and I'm giving away what that code is supposed to do, right? And I don't mean to pick on this one website, but I just put it up there so that we all understand, right? Beginner's book, right? This is for a beginner. And you look at that code, right? And I could tell you, right? I mean, anybody handed that code into me as in one of my classes, that would be an F, right? This would be a fail, right? I mean, and let me explain to you why, right? I mean, because, right, it doesn't do any of that stuff that's there, right? All of this stuff that we've talked about that's important, right? So let's see why, right? So first of all, look at those two snippets of code there, right? Right, we all recognize this, right? That's a swap operation. We're swapping two elements of a vector. But why are they writing the same code over and over again, right? Of course, that should be abstracted away in a function. Use the function n times instead of writing the code repeatedly n times, right? And then, right, there's these while loops inside here, right? So look, we have that. And that, right, what is that doing? Well, that's kind of looking for the first number that's less than or equal to the pivot, right, from the left-hand side, right? Okay. Right. Well, I'm sorry, for the greater than, right? So from the left-hand side. But that's a separate problem. That's not quick sorting, right? So if you're going to solve a separate problem, right, have a separate function to solve that problem, right? And the same thing with the other while loop below it, right? Now that's searching from the right side of the vector. Right? And you say, well, again, that's not quicksort. So this is kind of suggesting to students that, look, solve everything in one big spaghetti function, right? This is not what we want, right? So if we extract those things away, right, now we have some functions to do that, and our code starts to look a lot better. But still, right, we still have that while loop there, and that's a signal that some other problem is being solved, right? It's not just quicksort here. So what is that? Right? And you look at that and you say, well, we understand quicksort, right? So, this is the loop that, right, partitions the vector, right? Well, that's a separate problem, right? A separate function for that. And so if you do that, now your code looks like this. And now that reads like quicksort, right? And that reads, and you say, oh, okay, I get it, right? It's easier to understand, right? So look, right, originally, no abstraction, no modularity, no documentation, none of this stuff for beginners. Okay, so overall, right, the answer, has this been done? Overall, my answer is it has not been done, right? And, right, if you can open up almost any computer science textbook and it doesn't do that. Now, there's notable exceptions, right? The first one is the Wizard book, which I'm sure everybody at the Scheme workshop has read and loves and can recite verse and chapter, right? And so I like this book a lot, right? This is what got me hooked on functional programming back in the day. And I like it because it spent a lot of time with design, right? Explaining how the problem is solved, right? So I recall, right? I saw this function in there, right? And of course, I didn't put the name of the function too clearly there because I wanted to just talk about it, right? But to me, I looked at that function and what does that do? Well, it computes the power set of some set S, right? And, right, okay, so it's empty. The only subset is the empty set. And if not, okay, recursively process the rest of the list and then create the subset by taking those that don't have the first element and adding the first element to those that don't have their first element and then appending the whole thing together, right? And to me, that made perfect sense, right? I mean, I was like hooked, right? But, I tried for years to use this with my undergraduates and it wasn't working, right? Right. So first of all, they hit a brick wall when it came to this circular definition to recursion, right? They just couldn't get it. And many of them argued with me that all their life they've been told that circular definitions are bad and they should stay away from them, right? So this was one of the brick walls. And then, of course, this happens in chapter 1 of the book, right? So map, right? They didn't understand this abstraction, right? This generic function that works for many different types of data. That was another roadblock. Lambda, of course, functions as values. In chapter 1, this was again not something that's easily consumed. Now, maybe for the top 10, 15% of the students, they can manage, but the middle 50% of the students, right? Those are struggling with this, right? And then the type-driven design is not explicit, and there is no unit testing in SIGP. Okay, so how could we make that a little better, right? We can play with the code and we say, okay, well, let's define the type, right? So there it is. This is what a set of X is. It's either empty or the cons of an X in a set of X. And then, right, once you have that data definition, this function makes sense, right? Because, right, the self-reference becomes a recursive call, right? And to process something of type X, you call a function to process that type. Where is it? Just separate problem. But anyways, right? And then you could write tests, little print statements to illustrate, to validate but that's not modern, right? This is not how we do things today, right? So another notable exception is how to design programs, right? And then how to design programs kind of takes all of these ideas and unites them, right? So it has a lot of pros, right? It introduces systematic type-driven design, right? And about half of the book is dedicated to that, right? Structural recursion, right? Let's follow the shape of the data, tells you what the shape of your function should be. It has these wonderful domain-specific languages, specially made for students, that have great error messages that are comprehensible to students. Sorry, Simon, unlike Haskell, where you forget to put a plus and you get some error that says you broke the functor, right? I mean, right? So right. And then, right, it teaches syntax on a need-to-know basis. We don't just spring syntax onto them. We say, look, we need to do this. Now we need to learn more syntax. Okay, it has unit testing, which is wonderful. And it does functional abstraction, right? So it's beginning to teach students how to think abstractly. It emphasizes auxiliary functions. In other words, don't solve everything in one big spaghetti function. And then it tackles other forms of recursion, right? And it does that all in this book. And then the first edition would do mutation, but that was taken out of the second edition. So now, right, the book does not talk about mutation at all. And then the great thing, it's fun, right? It has animations in there. And students love this, right? Because they get to be creative, right? And don't underestimate the value of that, right? My solution to the problem doesn't look exactly like your solution, right? I can personalize my solution to the problem. And that goes far with students. And in my experience, especially with female undergraduate students who are unsure about majoring in computer science, right? They say, look, this is really encouraging that I can personalize and kind of put my creative thought into the programs that we write. Okay, so let's go back to the power set. So we define the type. Now, right, so what would happen at this point? You say, well, look, we can create a template because that data definition is screaming at us how the data should be processed, right? So, and that's what I was talking about before, right? You have something of type X, call a function, right? Call an auxiliary function that processes X. And then the self-reference is a recursive call. And then the name of the game, of course, is what? Specialize the template for whatever problem you're trying to solve. Right, so a lot of focus on design idea. You have to explain how you're going to compute the power set, right? Give an explanation. And once you do that, right, you write a function that might look like this, right? So this is a function that students have written, right? And makes sense, right? If it's empty, well, we return only the empty subset. And then, right, if it's not empty, well, we compute the power set of the rest because that's what the design, what the template tells us to do. And then we have to add the first element to each element of the power set of the rest, right? And then we write these wonderful tests and right? And then, of course, we have to write that auxiliary function, right? We have to add, that's a separate problem, write an auxiliary function. And you write the auxiliary function, right? In this case, we can use map. And, right, we have this program and we can run it, right? And it works and the tests pass. And then you say to yourself, right, you give it bigger input, and then all of a sudden it gets slow, right? And this is how we motivate new syntax, right? Because we say, look, we're computing the power set of the rest twice. This is wasteful. We shouldn't, just like we don't repeat codes, we shouldn't repeat computations. And so this motivates the use of local expressions or let expressions or whatever version you want to use, right? So that's how we motivate, right? And this is, right, and they do a wonderful job in how to design programs to do this, right? Right, so, but it has its downside. First of all, it's too heavy. It's too much to do in one semester, right? Students feel overwhelmed, right? I mean, once you finish structural recursion and functional abstraction, this jump to generative recursion, the intellectual leap is too big for most students in one semester, right? The other and the main problem for that is because all of a sudden the design recipe is no longer prescriptive. It doesn't tell you exactly where the function calls are, right? When you use generative recursion, you have to say, hey, look, I have to figure out how to do this. And so now they have to do two new things. They have to deal with a design recipe that's not prescriptive, and they have to figure out where the recursive calls and the function calls go, right? So two new problems, and it overwhelms students, right? And it also sidesteps the needs of other professors who are not into functional programming, right? The professors that are telling you, pardon me, but God damn it, I want to see objects and I want to see mutation in the first year curriculum, right? It also lacks a good iterative refinement example. Right? There's no big example that you can carry through the semester and say, as you learn more programming, we can make the solution better. Right? And it doesn't explain what functions are. And this is, right, this is a late realization that I've had because I was volunteering to help teach programming in inner city schools in Newark, New Jersey. And, right, the kids almost revolted when I said, write a function to do this. And they were like, what do you mean write a function? Yeah, write a function. And it said, come on, functions are always given to us. We don't have to write them. And I said, well, here you have to write them. And it says, anyway, where do functions come from? And that one question got me to think, right? They don't understand what functions are. Right? They've taken pre-calc and algebra, and some of them are in AP calculus, but they don't really understand what functions are. So they can plug in, they can graph a function, but they don't know where they come from. So they find it difficult to write their own functions. Right? So this is something I think we need to address. And then there's very little, if any, empirical motivation or studies or examples in how to design programs. Right, so how do we solve these problems, right? Well, we need to spread out the material, but what's in how to design programs is not enough for 2 semesters. It falls short, right? We need an easier transition to non-prescriptive design recipes, right? So we have to fill this gap in, find something that's not prescriptive, but where all the code that they write is still using the prescriptive design recipes, right? And here's where I'm going to try to be timely and relevant and introduce something new that traditionally has not been done by first year textbooks or courses. Okay. And I am going to listen to my colleagues and not brush them off. And I'm going to give them what they want. And I'm going to say, okay, you want objects? I'll give you objects. You want mutation? I'll give you mutation. But I'll do it in what? In a disciplined way, rigorous way. Not the nilly-willy way that's kind of taught in 98% of the textbooks in computer science. And if you're an author, I don't mean to pick on your textbook, please. Don't send me any hate email. We're going to include a good iterative refinement example. And for this, right, of course, there's nothing better than doing a video game, right? So we're going to take a video game from day one, and we're going to say, look, at the beginning, this video game, and I'm quoting my students, sucks. But by the end of the semester, when they've learned a lot about programming, now they have this great video game, and they can go home and say, hey, Mom, look what I can do, right? So it gives them this sense of accomplishment. And again, I don't think that should be underestimated. And to solve this problem of what are functions, I think that we need to introduce abstraction a lot earlier than how to design programs do. But also abstraction over functions, right? To create generic functions is too late. We need to do it really early in the curriculum. And then, of course, I want to introduce them to empirical experimentation. And this is where they have fun also, right? Because they can see the numbers and they can see what works and what doesn't work, right? And hopefully I'll show you an example where it should obviously work and it doesn't. Okay, so my solution is expressed in these two textbooks: Animated Problem Solving, which is already in print. And I was hoping that Animated Program Design would also be in print, but publishers work on their own schedule. So that should be out in October or November, I'm told now, right? So, okay, so what is it that we do there? Why is this new and fresh and relevant, right? So it spreads out the material, as I had said, right? And so the first volume, right, does all the basics: expressions, functions, conditionals. It introduces the video game Aliens Attack, which is a Space Invaders-like video game. Okay, and then we talk about, right, structures and data of arbitrary size and structural recursion and functional abstraction. They get to meet, right, all our friends, higher order functions like map and filter. And, right, they learn about curried functions. And then, right, this is where they get to learn about objects. We also do pattern matching, which is traditionally not done with beginning students, right? And then the book ends with distributed programming, where now they get to, right, write a distributed application by the end of the semester, right? And so they take Aliens Attack and they make a multiplayer game out of it. Okay, so the second volume starts where we left off with examples of distributed programming, and then it introduces students to randomness. And I thought that this is an important topic to introduce students to, because when they don't know how to do something, they immediately say, oh, just do it randomly. And so we have to teach them that randomness isn't really appropriate every time they don't know how to do something, right? So there's some principles of randomness. And then our iterative refinement long-term example is the end puzzle game, right? So, and then they have to learn how to solve this for the player, right? And so I'm going to talk about that a lot. And then, of course, we cover, right, to learn how to solve this puzzle, we need to learn about generative recursion. We need to learn about accumulative recursion, right? And then the book ends with mutation, again, trying to satisfy my colleagues who don't like functional programming. Yes?
Can you please explain what do you mean by students do it randomly? Like what exactly?
Students with what?
Like the randomness, distributed programming randomness. You mentioned it. Students, when they don't know something, they say, let's do it randomly. But what do you mean? Any example?
Okay, so for example, I'll talk about this in more detail, but with the end puzzle game, right, you have to make a move, right? The player requests the computer to make a move for them. And then they say, well, I don't know how to pick a move. Just pick a move randomly, right? And this is incorrect. So, right, they should use randomness if they're generating passwords or if they're trying to simulate random atomic decay. But they shouldn't be using randomness to make a move in a game like this. Right? Okay. And, right, so here's where we say we're become less prescriptive. And this paves the way to generative recursion, which is not prescriptive at all. And then we also introduce them to property-based testing. So the goal is always, look, try to sprinkle all these more advanced concepts with your beginners. They can do it, right? It can be done with undergraduates at all levels. Okay, so let's see. Yeah, I talked about giving the audience what they want, the professors what they want, and I talked about the games, yeah. Right, so the abstraction part, we start fairly early in the first volume because we teach them how to write expressions, and then we teach them that if you abstract over similar expressions, you get functions. And this is how they begin to understand where functions come from. And it has turned out to be extremely effective, right? It reduces this fear of having to write your own functions at the beginning. Okay, experimentation, right? All kinds of sorting, searching, right? The typical stuff that you would do in an algorithms course. We try to introduce students in the second volume of this book. So just imagine, right? So at this point, you're saying this is a lot, but just imagine, right? If a first-year student goes through something like this, what you can do up the curriculum with these students, right? Okay, so let's be beginners, right? So I'm going to ask you to, right, don't be advanced computer scientist, but try to remember when you were a first-year student or freshman or something, and let's be beginners. Imagine that we don't know very much about programming, right? And so here's the goal, right? We want to write aliens attack, right? So, right, everybody knows how Space Invaders works, correct? Right, okay. So, right, how do we do this, right? This is the problem. How do we do this, right? So you can learn a lot from a video game, believe it or not, right? Right, so consider moving a list of aliens, for example, right? So the first thing you have to do, well, what the heck is a list of aliens, right? So you have to define what a list of aliens is. We're going to say it's empty, or it's the cons of an alien with a list of aliens, right? So recursive data definition, you know what? It's screaming at us, hey, you need a recursive function template, right? So, but before that, if you make a data definition, hey, you write some sample instances of the data, illustrate what samples are, right? So you can write some examples of the data, and then you write your template, right? So for your template, right, you're going to show some expressions that compute the values, at least one expression for each subtype. So you have two subtypes, you need at least two sample expressions to say, look, here's how we compute an answer with these concrete values. And then, right, you can abstract over those and you get your function template, and you know that, well, okay, if you have to tell, you need a conditional because there's variety in the data. You need to tell which subtype you're processing. And then, of course, if it's empty, you do something. If it's not empty, then there's two things you have to do, right? If you look at that, the first thing is an alien. Call a function to process an alien. Don't even think about it. And then, right, recursively process the rest of the list of aliens. And then, of course, you have to have tests. And this is what we call a template in this curriculum, right? Everything is included. So it's not just the function definition, right? It's everything in one package. And then, right, you can use that to actually move a list of aliens, right? So if we move the empty list of aliens, well, we just return it. There's nothing to do there. But if it's not empty, then I have these two examples here. And I'm going to what? I'm going to move the first alien, move the rest of the aliens, and then cons them together. And at that moment, you see that these two expressions are extremely similar. And it's screaming abstraction, right? And so you're going to abstract that, and you're going to say, well, look, what are the differences? Well, the list of aliens and the direction that they're moving on. There's two differences. That is telling you, it's screaming at you, you need two parameters in your function, right? So we're going to have two parameters. There it is, my list of aliens and my direction. And now I can write some tests, right? So I write tests for the value of the sample expressions, and then we write tests for values that are not in the sample expressions. Okay, and then finally we specialize the body of the template, And right, as suggested, right, if it's empty, we just return empty, and otherwise, we take one of these expressions, plug it in, and substitute the concrete values with the variables. It's very mechanical, right? You just substitute, plug in, and students are good at plugging in, right? So, and there it is, right? Now you have a function to move a list of aliens, but it's not painful for the students to develop this because they're following a very systematic approach. And then, right, you ask them, okay, move a list of shots. Okay, you follow the same steps, right? You get your data definitions, your examples, your template, and now you specialize the template and you get a function that looks like that. Okay, and now something has happened, right? Because now if you look at the two functions, they look incredibly similar, right? They're not exactly the same, but they're incredibly similar. And you say, well, look, let's do functional abstraction. But in order to do that, of course, they have to be structurally the same. And here we're applying a function to one argument, and here we're applying a function to two arguments. So this gives us an opportunity to talk to them about code refactoring. Let's change the code a little bit so that they look similar, and now we can apply an abstraction step. And so, okay, so it's probably easier to work with the one that has more arguments. And if you think about it for a little bit, you say, well, I'm moving every alien in the same direction. So why don't I just compute a function to move an alien in that direction and then apply that function to the argument, to the first of the list. Okay, so let's do that. So there it is, right? Here's your make alien moving function, right? It returns a function, takes as input an alien, and moves it in the given direction. And now you can refactor, right, the original function and use that there. And now these two functions structurally look the same. And we can do functional abstraction, right? And so we're saying, well, let's see. If you abstract these two, right, we all know where this is going, right? You get map, right? And so now, right, you have map and students understand the abstraction, right? There's no doubt in their mind now what map is doing. And then what? Well, now we can rewrite the original functions and we have these beautiful code, one-liners, extremely powerful. But there's no mystery, right? So all that stuff that they do in SICP in chapter 1, we can't do it in chapter 1 because we need to get them to this point where they understand the abstraction. Okay. And believe it or not, another wonderful thing has happened, right? Look at that function. Now, of course, right, you're going to tell me, well, that's a function that returns a function. What's so wonderful about that? Well, okay, right? Well, again, put your beginning student cap on, right? You're computing a function, right? I mean, right? And so, right? So, but this is a courage function, right? So it's a special type of function. It consumes its input in stages, right? And now the wonderful thing is that once students learn about courage functions, you can talk to them about objects for free, right? So there it is, right? This is a class, make alien mover, that computes objects that know how to move an alien in a given direction, right? So let's play around with this a little bit. So what I'm going to do is I'm going to define some geometric shapes and try to write a program to process geometric shapes, right? So I'm going to define squares, rectangle, and circles. Each one of them have some number of characteristics, right? And I'm going to say a geometric shape is one of those three. Okay? Now we can think, right? We explain to the students, we can think of data as not just the values contained, but also the operations that are valid on that data type. And we package them all together with something that they've studied, a local expression, right? We encapsulate everything together. And to get services out of encapsulated data, we send messages, right? And so the messages tell us what you want to do, right? So similar to what the dot notation does in Java, right? So here are the services that I want. I want to be able to distinguish between the subtypes. I want to compute the area of a geometric shape. And I want to know if a geometric shape is bigger than another geometric shape. Okay, so for that, I need to define what the messages are. So here on the left-hand side are all the valid messages. And then on the right side, I define what's returned, the type of the return value. And so, of course, for the predicates, we return a Boolean. For the area, we return a number. But now if you need extra input, you return a function that consumes that extra input and then gives you the value that you're looking for. Okay, so if you know this now, you can write a template for the class. All right, so here's what it's going to look like. Right, we're going to make some geometric shape with whatever inputs are needed by the type of geometric shape. And we're going to have a function, right, that determines if this object is bigger than some given object. And then you have your message processing function, right, with all the valid messages there, and then what you have to do for each one of them. And you return the manager. So the object is that manager function. And now what you have to do is specialize that template for each subtype of geometric shape. Okay, well, here it is. Here's how we do it for square, right? So is square returns true, the others return false, right? The area of the square is just the square of the length. And then if it's bigger, I'm going to return my bigger function here that takes as input a geometric shape and then just compares the two areas, right? The area of this square with whatever area of the given geometric shape that's giving us input. Yeah, so we need to write this auxiliary function, but students are used to that. We'll get to that, right? And then you do exactly the same thing for the other two, for rectangles and circles. Right? And then, right, what I'm going to do, or what traditionally has been called, is we write wrapper functions to hide the details of message passing. Right? So this is what they would look like. So for example, here's where the area function is. We take our object that we get as input, we give it the message area, and voila, it computes the area function for us. Right? And for the bigger function, right, what do? Well, we take in two objects, and then, right, we send the message bigger to the first one. That returns that function that consumes the second object and tells us which one is bigger. Right? And now they've done the basics of object-oriented programming. In other words, right, they can move on to a course now where they can learn more abstractions offered by object-oriented programming. And then to test them, right, we can't compare functions. That's a no-no, right? We all know that's undecidable, unsolvable. So we have to test the services. So we test the wrapper functions. So they write unit tests in that way. Okay. And right, so once we have all this, right, we move on to the last part of this first course, which is distributed programming. And this is the design recipe that they're presented, right? So now you have to divide the program into the problem into components, right? Different computation entities. And then you draft data definitions for each one. And then you have new steps. You have to design a communication protocol, and you have to design marshalling or unmarshalling functions so that you can transmit data across the internet. And then you implement all the components and you test your program. And as you can see, right, this is not prescriptive. Nowhere there is it telling you where the function calls are or where the recursive calls are. But, right, everything that you do in steps 4 and 5 uses what? The design recipes that they've learned throughout the semester, right? So the only thing they have to deal with is the fact that this design recipe is not giving them all the details. They have to be a little bit more creative. Okay, so let's take a sense of what this is, right? This is the next refinement. This is what we want, right? So same as before, except that now we have our little yellow rockets, which are all our allies that are going to help us defeat the alien armada, right? Okay, so here's how we're going to divide the components, and I'm going to take one design that we do. So I'm going to design this from the perspective of a thick server, right? So all the real computation happens at the server. And so that's going to keep the state of the game, and it's going to manage all the worlds that are all the players that are connected to the server. And then the players, well, they only have to render the image of the game, and then they have to provide the user with a mechanism for moving the rocket and for shooting. Okay, right? So we're clear what each one of the components should do. And right? So here are our data definitions, right? The world or the state of the game will have a list of allies, a list of aliens, a direction for the aliens to move in, a list of shots, and a flag to detect if the game is over. And then the server needs something else. It needs the state of the game, which is a world, right? But it also needs a list of all the worlds or all the players that are connected to the server, right? So if you look at that, wow, 2 structures, right? That was done back in the beginning of the semester, right? So the students are not overwhelmed by looking at some structures here. Okay, right? So when should, right? We have to design this communication protocol. And we ask ourselves, when should the world send the message, right? Well, clearly, right? If the player moves his rocket or her rocket, you want to send the message. And if the player shoots, you want to send the message, right? So that's what we do. And then we say, okay, now we have to figure out how messages are exchanged, right? Outline how the messages are exchanged. And so they draw these communication protocols. And we say, well, look, if player I moves the rocket, well, send the rocket move message that contains the direction of the move to the server. And the server updates the state of the game. And what does it do? It sends that new updated state to all of the players. And then you do exactly the same thing for a shot, right? New shot message, but now it contains something that represents the shot and then updates the state, and the server sends out the new world to all the players. And if you look at these communication protocols, right, they're not overwhelming, right? In other words, we keep it simple, right, for first semester students. And then you ask yourselves, when should the server send a message? And this gets a little bit more complicated because there's more cases, right? So, of course, when something changes in the state, you send a message. We already saw that part. But also, when there's a new player who joins, that means we have a new ally. Update the state, send it out. When the world disconnects, that means we have one fewer ally. Update the state, send it out. And then, of course, when the clock ticks, because everything moves, the aliens move, the rockets move, the direction can change. Okay, and the communication protocols look incredibly simple, right? Some event happens, a new player comes in, send out the new world. A player disconnects, send out the new world. The clock ticks, update the state, send out the new state to all the players, right? So again, right, my point is we're trying not to be overwhelming with beginners, right? Okay, and so now, right, we have all these messages, we have to define what they are. And this is a step that they're familiar with, right? You need data definitions, right? So we say, okay, what's a to-server message? And you say, well, a rocket move will have it'll be a list that has the tag rocket move and the string representing the direction that you want the rocket to move in. Okay, and what else do we need here? Well, we need to be able to create that type of message. So to marshal a rocket move, we take as input a direction and create that type of list. Right? And that code goes where? At the beginning of the arrow. So that we know that that's what? Player code. Now, what do we need at the end of the arrow? Well, right, we need to unmarshal that type of code. So the unmarshaling function simply what? Takes the second element out of the message. And it says this is the direction that you need. Right? And then we do the same thing for a rocket. Well, sorry, for a shot. But here it's different because a shot has an X and Y. Right? So we need 2 things. So we're going to create a list that looks like this, right? A tag and the X and Y coordinates. And then to marshal that, we take as input a shot and we create a list with the X and the Y of the shot. And then to unmarshal that, right, we create the shot again, which is just a posin, and with the second and third elements. Right, and this gives you a flavor of how simple the functions are that students have to write within this more complex application. Okay, so I'm going to skip the world because that's straightforward for everybody here. Okay, and then we have to write our message processing functions. Right, so to process a two-player message is fairly simple because there's only one, a world. The only thing you have to do is unmarshal it, and that becomes a new world. And at the server side, there's what, 2 types. I'm just going to do one here. So if it's a rocket move message, what are you going to do? You're going to define a new state for the game where you move the right ally and leave all the other components unchanged. And then, of course, right, you don't change the universe, but you use that new state that you just computed. And then you have to send all those messages, that new world out to all the players. So for that, we process our universe with map, and we just have a function that creates a mail for each world in the universe. And that's it, right? And if we look at that, right, let's take a little time to just see what the result is. But here we go. Right, so I can run the server and let me run the first player and let me run the second player. Right, so there we go. And you can see that the game is going, and we have 2 different players, and of course we can move, and you can see that, right, the shots appear in both, and I could do the same for the other. And students go home and, right, as I said, hey mom, look what I can do, right? And this is what they develop, right? And it doesn't matter what student you are, that's exciting, right? Even if you don't like video games, to be able to do something like that, right, is just exciting. Okay. Okay, I'm running late, I know. So let's move on to what we do after that. Okay. Oof. There we go. Right, so in the next semester, we use this as our motivation, the end puzzle game. Right, so now they have to write an application where they have to solve this puzzle, right? Okay, so what does it mean to find a solution, right? And you say, well, we have this board B as input, and we have to find all the steps to get to the winning board. And how do you do that? Well, you take one of the successors of your board B and find a solution of all the moves to the win from that board. But now they've discovered something, right? This is no longer structural recursion. This is generative recursion, because the new board, the successor of your input, is not part of the structure of the input board, right? So now, right, this motivates the study of generative recursion. And so they'll go away, we'll go away, and we'll study generative recursion. And then we come back to the question, how do you pick a successor? And the first thing that comes to mind is do it randomly, right? And I say, okay, let's see. So we're going to compute, we're going to figure out where the blank space is, we're going to get the neighbors of the blank space, and then we're going to swap 2 tiles, the blank space, which is indexed by P, with what? Some random neighbor of the blank space, right? Okay, sounds reasonable. Not really, right? Because it's slow at best and it runs out of memory frequently, right? And I have to tell you, a video game that doesn't work, that's the worst thing, right? There's nothing worse in the world than that, right? So we need to do better, right? So we do generative recursion and we say, okay, well, look, we can do depth first search to do this, right? So what do? We generate the children, right? The successors of the board that we get as input. And then, right, we're going to use a heuristic to find the best of those children and continue the search with the best child. Forget all the other children, right? And of course, let's run it. And you'll say, oh, it goes into an infinite recursion. That didn't work, right? And so we study why it didn't work, and students discover loss of knowledge and the need to have accumulators, to remember stuff that they need to avoid that type of problem, right? So this motivates a cumulative recursion, right? And so now, once they learn about a cumulative recursion, you'll say, hey, let's do breadth first search, right? And so with breadth first search, what we're going to do is we're going to remember all the paths. We're not going to ignore any of the children, any of the successors, right? So we generate the successors, and then we create a new path for each one of those, and then we add those to our accumulator of paths, and continue the search that way until one of those paths reaches a win. And this is guaranteed to halt, right? To find a solution. And of course, let's run it. And it's extremely slow, right? Right. And again, nothing worse than a slow video game, right? So now what do we do? So now, right, this is where I take the opportunity to throw a little AI into the first year curriculum, right? So we teach them about A star, right? So we use our heuristic that we were using for depth first search, and now we use it for A star. And what we say is, look, we're going to find the neighbors, but we're not going to create new paths for boards that have already been visited. We're going to only use the unvisited ones. And then we're going to explore the path that's most promising, the one that heuristic tells us is the best, right? Right. So, where am I? New path. Yeah. So we're going to create these new paths, and then we're going to remove the best path and then append, right? Okay. And so now we say, let's run this, right? And here's where students get excited now, because after all this work, going through all these iterative versions, right, they get to run experiments and they see this, right? And then they begin to understand why depth first search is so slow, right? Because if you need to make 26,000 moves to find a solution, it's going really deep into the search space. That's why it's slow, right? Right, and then they can see that breadth first search is usually faster, but not always, right? Sometimes depth first search is faster here, right? And then they see, but A star is the king, right? It just blows away everything else, right? And this, believe it or not, this is exciting for students, right? Okay, and then we go into a mutation. I'm going to do it in 2 minutes. Delayed operation for factorial, we all know that. Eliminate it using an accumulator. And then you say, right, okay, what's the difference? That's the trace, right? A lot of work being done by with the delayed operation. If you look at the accumulative recursion, you only need 2 stages, right? There's less work being done. And you say, clearly, accumulative recursion in this case should be faster. Well, let's time it. Turns out it's not, right? So this motivates the need for always empirical experimentation, right? Right. Of course, there might be some optimizations going on underneath the hood that make the structural recursion version faster. Okay, and then we can think of it as mutations instead of recursive calls, and then we have to decide in what order the mutation should be done. And this is something that's rarely taught. And of course, this motivates the use of OR logic and to how to mutate mutations correctly. So a little bit of rigor, right? And so we introduce them to while loops. And we introduce the basic idea: achieve the invariant with the initial set of mutations. Then you have your while loop, and you drag the invariant through the mutations. Make sure that you end up that the invariant is maintained, and then you use the invariant in the negation of the driver to decide what value should be returned, right? This is the hardest part of the course, by the way, right? But hey, students who actually put in the time really turn in code that's bug-free, right? And so and these students appreciate that. So where do we go now? Vertical integration, right? Just imagine what you can do if you have an army of first-year students who have gone through a curriculum like this, right? And so my candidate has been the formal languages and automata theory course, right? Because it's about programming, right? You create these state machines, right? Architecture. You have constructive proofs, which means what? Designing algorithms. And you have formal reasoning, right? And you say, well, why is this pencil and paper? If it's about programming, why is it about always done pencil and paper? And so we say, right, and then on top of that, right, I have seen students spend all kinds of time trying to draw machines. And I say, well, we have technology for this. Why are the students wasting time drawing machines, right? So I say functional programming to the rescue, right? Here we go, right? And we say, okay, I've developed a DSL called FSM, stands for Functional State Machines. where each type of machine, a deterministic, finite automata, a Turing machine, a push-down automata, are types as well as grammars. So context-free, regular, context-sensitive. These are all types in FSM. And you can execute, and you can visualize how the machine works. Plus, you can test that it's correct because you can write invariants for your states and then see that those invariants hold as execution proceeds, right? And FSM also allows you to implement all the algorithms that you develop as part of your constructive proofs. Okay, so let's consider this small language. You have an even number of A's and an odd number of B's. And how do you design a machine to do this? The key, again, is design. Well, you see at the beginning, there's 0 A's and 0 B's. So that's even. And then if you read an A, you have what? Odd A's and even B's. So that will be state A. And then if you read a B, right, you'll have even A's and odd B's. Well, that's the final state, F. And then, of course, you could have odd and odd, right? And that would be state B. And now you can write, right? If you know what the states represent, you can write an invariant. So for example, here's the invariant for the S state, right? We extract the A's and the B's, simple. And then we just make sure that both lengths are even, right? And here's how you implement this machine in FSM, right? Here are a list of states, the alphabet, the starting state, the list of final states, and the transitions. You have to design the transitions, right? So even, and you read an A, now you're odd even. If you read a B, you're what? Even, odd, right? And you design this for each one of those states. And let's take a look at how this magic works. All right. Oops. Here we go. Right, so I'm just going to run my machine that we just defined with all its invariants. And we get something that looks like this. Right, so this is what the control view of the machine is. Let me give it some input. Right, so let me run this. And then, right, you see that this arrow appears, and if the arrow is green, the invariant holds. If the arrow is red, the invariant fails. And if it's orange, it means your invariant is invalid. Yeah. Okay, and then you can just step through it, and as you step, you can see the color of the arrow. And for those of you, again, talking to my colleagues who don't like control view, right, if you insist on having a transition diagram, you can do that also. And you can see that the states change color, right? So in a nutshell, that gives you a small taste of what we can do with functional programming. And it simplifies, right, a lot of the stuff. And it makes, right, it's turned out that this course has become popular now with students, right? Because it's right, they get to do programming in it. Right? Okay, so can we do all of this wonderful stuff? Yes, right? And we can do it effectively. And this is why functional programming is important in computer science education. Okay, whoops, wrong direction. So we're going to skip that because I ran out of time. I have one plug, right? TFP and TFPIE are going to be held in Boston in January. So please come, give us a talk, right? Send us whether it's publication ripe or half-baked or just a beginning thought, right? Submit a little abstract, come give us a talk, right? If you decide you want to submit it for review, it happens after the conference. So, right, you can take all the feedback that you get in the conference and put it in your paper and then review, right? So it's in Boston right before POPL. So you can get three nice conferences in one trip here. Okay, so on that note, any questions?